And now for our second lesson of this week. What we've been doing this entire last few weeks, we've been graphing these things called relations. So our first definition of several today is that of a relation. A relation is any set of ordered pairs. And mathematically, that definition has a number of things going on with it as well. A set we can think of as a collection. Ordered pairs refer to any number of xy's that we can think of. So if I kind of make a set of ordered pairs, I can make the ordered pair 1, 3, 2, 7, 3, 8. I'm just making these up, but these are relations. It's a set of ordered pairs. For some reason, there is now meaning between the numbers 1 and 3. There's meaning between the numbers 2 and 7 and 3 and 8. I've created that meaning because I made up these ordered pairs. I can also represent this relation in another way. I could do it by t-chart. I could say, here's xy, and let's list them off. 1, 3, 2, 7, 3, 8. I can also represent that with a diagram. I'll put 1, 2, 3, I'll put 3, 7, 8, and I'm going to match. 1 goes to 3, 2 goes to 7, 3 goes to 8. Those are just a few ways that I can represent this relation. So we kind of characterize now all these numbers into whether they go on the left or whether they go on the right, whether it's an x or whether it's a y. So today you have the privilege of learning about one of the most important concepts of not Algebra 1, but Algebra 2 and pre-calculus. Yes, we introduce it now, though, because this is important that's coming down the road. You've heard this word before, a domain. A domain is the set of all possible first coordinates. All possible first coordinates. It actually has an old-fashioned word associated with it. It's called abscissa. A domain value could be called an abscissa. So I can actually say abscissas, plural. So all possible first coordinates. If I look up above, I can say that my domain here was the number 1, the number 2, and the number 3. Those were all the possible first coordinates of the one I did. Another example is I can look at this as equal to 2x plus 7. That's a line. If you think about a line, there's no limitation, there's no restriction for what I could plug into x. I can plug anything, any real number, into x. X represents the domain, so that would mean my domain here is all real numbers. Here's yet another example. Let's say y is equal to 1 over x minus 1. Here, I cannot plug anything into x. There's actually one number that I cannot plug into x. So my domain would have to be all x such that, and then I get to say x cannot be equal to, dramatic pause, 1. Because if I plugged 1 in, it would have 1 over 0. You can never divide by 0, even in the comfort of your own homes, so don't do it. That is domain. Domain's the easier of the two, but it's the one that we focus on more so than the other one. So what's the other one? Well, the opposite of domain would be a range. Range is the set of all possible second coordinates. That has an old-fashioned name of ordinates. So, all possible second coordinates. Now, we're not going to deal yet with domain from an equation perspective. But we are going to deal with domain from, with range from scale. We're going to deal with range from just kind of ordered pairs. But if I look back up, I would be able to say that the range of this thing, I want a different color. But the range of this thing would be all the second ones, so all of these. And those would have values of 3, 7, and 8. Please note that listing domain and range, I'm going to go back up here, listing domain and range does not tell you how they're matched up. It's just listing. What are all the possible x values? What are all the possible y values? So, let's go to a neutral color. Let's go black. Okay, big example here. I'm going to do the ordered pair. 0, -7, 0, 1, and 15, 4. Those are 4 ordered pairs, but I put those ordered pairs in set notation. You can actually put ordered pairs in set notation, just like you can put individual numbers. My domain is all the possible x's. Now, we never repeat values in the domain. So if I look, I have 5, 0, 0 again, so I'm not going to use that, and 15. That's my domain. And you may say, well, they're not. Those aren't in order. Okay. Range. 1, -7. 1's already there. And 4. So, if I were to cover up, and yeah, I can do this. If I were to cover up what I just did and look at my domain range, I would never be able to tell what those original ordered pairs were. So just kind of keep that in mind. Domain range is not a substitute for listing those pairs. It's just an attribute. It's a quality. Something about them. Okay, so going back to relations. I could say any number of things about relations, but what we really want to hone in on are functions. I am evil. I'm going to make you memorize something. You will have to memorize this because I did. So big definition. This is one that I make everyone memorize. Algebra 1, Algebra 2, Algebra 2 honors, pre-calculus. You will have to memorize this. The definition of a function. A function is a type of relation, a special type of relation, but a type of relation in which each element of the domain, all possible x's, is mapped to. Now I could say mapped to, I could say transformed into, which is a little bit more visual, but is mapped to, or even paired with, but is mapped to, transformed into, paired with, one and only one elements of the range. That is a function. Now, I love synonyms. I love this idea of the mapped to, transformed into, paired with, can be thought of in multiple ways, because that gives us different ways we can visualize this. But pretty much what a function is I want an answer to a question. I want you to tell me definitely, what does x become? And I need an answer. I don't need two answers. I need one answer. I need to know what x becomes. Because on a larger scale, let's take the example of the weather. I should be able to plug in a ton of variables and get out a single result. Will it rain? Yes or no? Not yes and no. I want to know yes or no, what will happen. That's kind of the basis behind a function. So it's a transformation. It is a rule. It is a mapping. Let's look at it from a rule perspective. Let's say that I have this function. This is going to be an example. And f is the rule that changes x into 7x minus 2. And that's literally what this means. It means f is the rule that changes x into 7x minus 2. Let's say I have that, and then let's say that my domain is -3, -50, and 2. Can you find the range? Do me a favor, pause this video after I write these numbers down, or after I write these addresses down, and just find the range. 2 or 3, hit pause right now. Okay, hopefully you hit pause. I'm going to erase this and go back to say, what's the range? Well, my range would be -3 minus 2, or -23. Over here I'll do that 7 times -3 minus 2. Then I'm going to want to do 7 times -50 minus 2. So my second one would be -350 minus 2. Then I'm going to want to do 7 times 2 minus 2, which gives me 12. Here's my range. Now, I don't have to use the letter F. I could use another letter, like G. And I could say that G is a different rule. Maybe G is the rule that says to take the number y and change y into y squared plus another y. Okay. Well, regardless of the fact that I'm using y and not x, the way that this is written says that we're going to change one number into another number. So it really doesn't matter what variables we use, the concept's the same. Here's my domain, 0, -3, +3, and 2. Okay, go ahead. Let's figure out what the range is. If this is the domain, and I want to find the range, I'm going to plug each of those values in. Let's start with 0, 0 squared plus 0. Then I'm going to do -3 squared plus a -3, +3 squared plus 3, and 2 squared plus 2. 0 squared plus 0 is 0. -3 is 6. 3 squared is 9. Plus 3 is 12. 2 squared is 4. Plus 2 is 6. This brings up an interesting point about functions. If you look at it, there were two values that I was able to plug in. The -3, come on highlighter, -3 and +2, both obtained 6. And if I really want to be correct in terms of the range, I shouldn't include this last 6 because I already included 6. This means that we can actually diagram this in another way. If I want to describe domain range, I could put, here's a domain, and here's the range. And sometimes we even represent this with arrows. 0 went to 0, -3 goes to 6, 3 goes to 12, and 2 goes to right back to 6. So this is a function. It's a function because I know exactly what every piece of the domain becomes. Even though -3 and 2 both went to 6, if you were to ask me, what does -3 become, I could give you a definite answer. The other case of where it's not a function, so I'm going to put here and say this is a function. It is also a function because I actually had a rule that told me what it becomes, and that's part of the very definition of a function. If you have a rule that says exactly what your input becomes, then you're fine. We're going to talk more on Monday about what a not a function means. But let me show this another way. Another big example. Okay, I'm going to start redefining f now. F doesn't always have to be the same thing. But instead of using the arrow notation, I'm going to say f of x equals 4x plus 2. And then I'm going to say g of x equals x squared minus 2x. And now let's go do some examples. Put into f of negative 14, g of negative 4, g of 1/5. Let's do d. D is going to be f of 3/4. Then we're going to do 1/3 times g of negative 2. And then we're going to do 2 times f of a minus 3. So, a lot of stuff going on here. Let's go back to the first one. F of negative 14. This means I'm going to substitute negative 14 into the f function. So 4 times negative 14 plus 2. It does not mean f times negative 14. That is different. So, looking at this, let me add some space here. I'm probably going to want some space over here too. 4 times negative 14 is negative 56, so then I have negative 56 plus 2, or negative 54. What this also means, FYI, is that I've actually generated an ordered pair. My ordered pair would be negative 14 and negative 54. Now, the answer to the question, the thing you would circle is this, because this is saying, what is f of negative 14? And you would say f of negative 14 is the same thing as negative 54. But this is kind of a little BTW, by the way. Just to keep in the back of your heads, this is actually an ordered pair. Negative 14, negative 54. Okay. G of negative 4 goes into the g function. So this is negative 4 parentheses square minus 2 times negative 4. I cannot emphasize enough putting those parentheses in so you see it's actually negative 4 being squared, and it becomes positive 16, not negative 16. Too many people rush this, and they say, oh, it's negative 4 squared. Oh, negative 16. I want to kill them. Okay, plus 8, 2 negatives make a positive, equals 24. G of positive 1/5. So let's do 1/5 squared minus 2 times 1/5. 1/5 squared is the same thing as 1/5 times 1/5. And this would be minus 2/5. 1/5 times 1/5 is 1/25 minus 2/5. And that's the same thing as 1/25 minus, let's change this into 10/25. And I get negative 9/25 as a final. Moving back up, we have part D. Part D says to do f of 3/4. So that's 4 times 3/4 plus 2, or 3 plus 2, or 5. Part E, I have 1/3 times g of negative 2. G of negative 2 is to take negative 2, plug it into the f function, or the g function. So I have 1/3 times negative 2 squared is 4. Then this would be plus 4. Move down. And that's 8/8. Okay, last one. Got an a minus 3. Don't let that throw you. This is still 2 times. But the way I'm going to deal with this is I'm actually just going to do some substitution. The f function says, highlighter come, it says take 4, multiply it by whatever you're plugging in, and add 2. So we're going to do the same thing with the a minus 3. We're going to take the 4, multiply it by a minus 3, then add 2. And now I'm just going to simplify. Still have the 2 on the outside. We're going to deal with that later. 4a minus 12 plus 2. Keep order of operations going. I have 2, 4a minus 10. And now I'm going to distribute the 2. 8a minus 20. Done.